With the OSIRIS-REx mission, NASA will do something that it has never done before: collect and return a bit of dust from one of the solar system's small asteroids. It's a rocky relic named Bennu. Bennu resembles two giant rocky cones that have been smashed together, creating an asteroid that's roughly the height of the Empire State Building. It carries what may be the very dust that made the planets and the very molecules that led to life on Earth. NASA's spacecraft, OSIRIS-REx, plans to collect at least 60 grams of the asteroid's dusty surface to ship back to Earth. But to get even a sample from a small body like Bennu is not easy. The first challenge is gravity. Gravity on a fairly big body like the Moon is a fraction of Earth's. In the Moon's case, it's about 1/6. But that's still a heavy tug compared with comets and asteroids, which can be 1/80,000th of Earth's gravity. Bennu's gravity is 1/10,000th that of Earth's. To stay in orbit or touch the surface, OSIRIS-REx can't move quickly. In fact, it needs to move only a few times faster than a slithering snail. When OSIRIS-REx heads toward the surface, it can gently glide down, sample, and with a slight push, go. The second and bigger challenge is finding a safe place to sample. Many small bodies, including Bennu, are rubble piles, heaps of rocks that pulled together from their mutual gravity. Everything from microscopic dust grains to house-sized boulders cover the asteroid, leaving almost no flat surface for the spacecraft to touch down. So, how do you safely collect a sample from these solar system lightweights? For OSIRIS-REx, NASA turned to the Small Body Mapping Tool. It's a program designed at the Johns Hopkins Applied Physics Laboratory in Maryland. The program can take images and other surface data collected by the spacecraft and project them onto a 3D object that's shaped like the asteroid. In the case of Bennu, the program combined 3D maps of the asteroid's surface that were made using two techniques. The first technique looks at how shadows and surface brightness change on a crater, boulder, or other surface feature on the asteroid during the day. That information can be used to determine a feature's shape, curvature, and slope. It can even find cracks or pebbles that are less than 1 inch long. The other method comes from a laser instrument called the OSIRIS-REx Laser Altimeter, or OLA. OLA scans sections of Bennu's surface dozens of times, determining the height of each feature by how long it takes a laser beam to return from that spot. Scientists at APL and York University in Canada used these scans to triangulate points on the surface. They then turned these points into a 3D cloud shaped like the surface. Both of these techniques can be used to distinguish large rocks that the spacecraft needs to avoid from smooth areas it can sample. When combined with APL's Small Body Mapping Tool, these maps create a complete 3D reconstruction of the asteroid's surface. Every bump, pebble, and crevice can be seen within inches of its actual location. This is how NASA identified the few places safe enough for OSIRIS-REx to sample, including Nightingale, the crater where the spacecraft will briefly touch down. But the 3D maps were also key to helping tell the spacecraft how to get to the sample site without any instruction. Scientists and engineers typically rely on gravity to help steer a spacecraft to the correct position when landing on a planet. But on Bennu, where gravity is weak, that method just wouldn't fly. Instead, engineers identified waypoints on the surface of Bennu. APL scientists, with colleagues from the Planetary Science Institute and York University, built 3D maps of these landmarks. These maps are embedded in OSIRIS-REx. When the spacecraft flies over Bennu, it can compare the surface below with its onboard model. As it finds the waypoints, the spacecraft automatically adjusts itself until it flies to the sample site. OSIRIS-REx will be the first spacecraft to ever use such autonomous technology to collect a sample. Scientists have found a clever way to navigate and safely land on one of the solar system's lightweights. In doing so, they may uncover how both the solar system and life itself came to be.